Hey there, in this video we're going to talk about pointers. Pointers are pretty notorious for being a difficult subject for C and C++ students, but once you get the hang of them, it's really not too bad. So we're going to get some practice here, maybe do a little bit of exploring, and I urge you to do the same, and eventually you'll have it conceptualized in a way that makes sense to you. We'll start off with some definitions here. Two terms that you hear used interchangeably are pointer and memory address. Now, technically, memory address is just a way to locate something in RAM. It's typically a long hexadecimal number, and it tells us at which byte we can find the data we're looking for. So it's pretty simple. A memory address is pretty simple. Pointer has a little bit more information. So a pointer is a variable that typically holds a memory address. So it can also hold null, which indicates it has no memory address. And it can also hold things that are not valid memory addresses. But typically a pointer does hold a memory address, so it's fair to use the terms pretty much interchangeably. Pointers also have a type. So if you have an int pointer, that means your pointer is referring to int data, whereas a memory address doesn't necessarily imply what kind of data is there. Okay, so let's take a look at a little bit of the syntax we'll need. Now each one of them has a number of uses in C++. We're only going to see 3 specific scenarios here. So let's pull up our demo program here, pointer test. So if you throw an ampersand in front of a variable, let's create an int variable here, we'll call it x and store 5 in it. If I was to throw an ampersand in front of an x, that would refer to the address of x, or a way to refer to x in memory. So that's the only use we're going to see for ampersand. You can also use that for bitwise and you can use it to create reference variables in C++, but we're going to use it only to get the address of a particular variable. We'll also see using an asterisk in front of a variable declaration. So when I'm creating a variable, if I put a star in front of the variable name, it's going to indicate that that variable is a pointer. Whereas later on, if I were to put a star in front of that variable, pre-existing variable, that star indicates the dereference operator, which is sort of the opposite of the address operator. So this is sort of the opposite of this. We'll see an example of that in just a second. And of course, the star is used for multiplication as well. But yeah, so we've got the ampersand for address of, we've got the star for creating pointers in a declaration, and also for dereferencing pointers, which sort of undoes the address. It actually goes to the data. So let's take a look at our example here. I have an integer variable, x, and I've stored 5 into it. Now I'm also going to create a pointer variable here. Now because this points to an int, I am first going to write int. That's the base type right here. And because I also want it to be a pointer, I'm going to put the star modifier in front of the variable name. So I can say int star p. That says p is a pointer to an integer. Now, you might wonder why the star is not next to the data type, like the base type right there, because personally I think that would make more sense. If p is an integer pointer, integer pointers should be, the whole type should be grouped together. However, that's not the case. If I were to do something like this, actually, if I chose to do something like this, P1 and P2, P1 would be a pointer to an int, and P2 would be a regular integer, because that star only modifies the variable that it's right next to. So that's why we put the star right next to that variable name, just to be very clear as to what's being made a pointer. So I just created a pointer to an integer, and it's called p. And in this pointer variable, I can store a memory address. Well, what memory address am I going to store in here? Well, I've got one other variable as a candidate, so let's get the address of x and store that in here. And for that, we can use our ampersand. So now we have x, which has 5 in it, and p, which has the address of x in it. Now to see what's going on, let's go ahead and add some output. I'm going to say at address, and I'm going to actually say what the address is of x just so I can verify, at this address, then I will say x is equal to, and then I'll print out x. Because every variable is stored at an address, and I'm also printing the value of x here. And I'm actually just going to copy this line, and I'm going to say at address, and then I'll give the address of the variable p. Even though p is a pointer and it holds a memory address, it has its own memory address as well. That can be a little bit confusing, but pointers store a memory address and they have their own memory address. So I'm going to print out the address of p, and I'm going to say what p stores here. So let's run this. With any luck, I did not make any errors. So far, so good. All right, cool. So we see at address BF9133E8, I have a variable x with the value 5, and at address BF9133EC, I have a variable p with the value BF9133E8. You notice the variables are stored next to each other in memory. This is something C++ does whenever you create stack variables, like we did there. X and p are both stack variables. They are created right next to each other in memory. So let's see how close exactly they are. So x is at E8 and p is at EC. So the difference between 8 and C, you have to know a little bit about hexadecimal here, but we can count up 9. So from starting at 8, 9, A, B, C. So that's a distance of 4 different addresses. Well, the reason for that is an integer takes up 4 bytes on this particular system. So the next variable is going to store its data 4 bytes after the address of x. That can come in handy to keep in mind later on when you start working with memory and moving pointers around in memory. So let's also take a look at what this would look like if we were to draw this out. So we've got, let's see, x is at 3. I'm going to shorten the addresses. So I'll do x is at 3E8 and p is at 3EC. So I can represent 3E8 here and 3EC. So this is my memory. It'd be my RAM over here. And we know at 3E8, we need a symbol table as well because we can't really refer to them by name unless we say, so X is stored at this particular memory address right here. Or let's do that again. X is stored at this particular memory address right here. And P is stored at this memory address here. All right, so in X we stored 5. And in P, you see we stored the address of X, which is 3E8. All right, so that's what's going on. Again, P has its own address and it has its own data, which happens to be the address of 5. All right, now we're going to add in a dereferencing operation here. So we've seen 2 of these symbols we're going to use. We know about the ampersand to get the address. We know the star to declare a pointer. Now we need to learn about the dereference variable. The dereference operator simply goes to that address. So if I were to say, let's go ahead and comment these 2 lines out. And then I can say, and you know the dereference operator goes before a pointer. So I'm going to say P points to this value. And I will print out the dereferenced P. So what that's going to do is follow the pointer and get the data at that address. So visually, it's going to find P. And when I say star P, it's actually going to find that address right there, 3E8, which is right up here, and it's going to get this value. So when I say star P, it's going to follow that pointer, which is stored in the actual data, and return 5. So I should be seeing P points to this value, 5. Okay, let's try it out. Nice. So that is the dereference operator. So essentially, we've got some equivalencies here. And let me show you what I mean here. So we already know that star p is essentially the same as x, right? Because if you follow your pointer to that address, you're going to get the same value as x. So let me try this. I'm going to print out star p, and I'm going to print out x. And I'm also going to print out p, and think right now what the equivalent of p would be in terms of x before I write it down. If you guessed ampersand x, you are spot on. Because ampersand x will get the address of x, and that's what we stored into p here. So we should see 5 here, 5 here, and then that 3E8 address and that 3E8 address here. Now it's worth noting I actually may not get the same addresses the second time, and you almost certainly won't get the same addresses on your system. The addresses are something that are determined at runtime. Yeah, and you see I did get a completely different set of addresses here, but that's all right. They match, and that's all I care about. All right, so something else nice that you can do with the dereferencing operator, since I can do pretty much anything I would do with the normal x variable, I can also do with the dereferenced p. So let's say I wanted to add 1. So I could say, I'm going to go ahead and wipe these out. Oops. I can say x plus 1 is, and I'm actually going to do dereferenced p plus 1 here. And that should, and actually, you know, I'll just go ahead and tell you that's going to be 6 right there. Let's actually modify this though. I can set the current x value. I can add 1 to the current x value. So I can say p equals star p plus 1. And this would be exactly the same as if you were to say x equals x plus 1. But I'm going to do star p equals star p plus 1. X is now, I can do star p, and actually I'll print out x here to show you that star p actually modified that original x value. Cool, huh? And we can mix and match here as well. You don't always have, I mean, in this case, there's no point to have a pointer to x, but we can actually refer to it as x or star p. So I can also say, after this, I'll do x equals, or I'll do x plus plus, how about? And then I'll say x is now, so this should say, we'll add 1 up here too. X is now 5, x is now 6, and x is now 7, right? Voila. All right. So to recap, just one last time to make sure we got this. When you're declaring a type, star creates it as a pointer to an int, or a pointer to whatever. You could have a pointer to a char. The ampersand will get the address of a pre-existing variable. And the star on a pre-existing variable will actually go to that original variable. It'll refer to that original spot in memory. Now, you might wonder why we need to say a reference to an int. Why can't we just have a plain old pointer type? Because really, if it's just holding a memory address, then we don't need to know the type. Well, when we dereference, we do want to know the type because you need to know how to interpret it. C++ or C needs to know how to interpret that original data. So when you dereference P down here, it knows that it's referring to an integer, whereas otherwise it wouldn't. There is such thing as a void pointer, but you need to cast it to a particular, whatever pointer type you want to interpret it as before you use it. All right, I'm going to do one other little experiment here. I'm going to introduce a bug. in the same way that I did x++, I'm going to try star p++. Based on what we learned, this should pretty much be the same. I'm just essentially replacing x with star p. And based on what we know, it's pretty much exactly the same thing. So I should now see x's 5, 6, 7, and 8. But let's run this and see what bug I added. No compile errors. But at runtime, x did not increment there. Why on earth? Well, let's open it up in the debugger. First, I need to recompile with the G flag so it can be opened in the debugger. And I will say gdb pointer test. And let's take a look at the code, see what line we'll break at. I'm going to break here right at the end just to inspect some different variables actually, let's break here at line 11, okay? I can type B for break, line 11, and I'll run it. So here at line 11, let's just inspect our two variables. So, and first let's think about what we expect. At line 11, x should be 5, and p should be, well, we don't know what to expect, but we'll take a look. So I can print out x, it's 5. I can print out p, and I get a value of something, 668. All right, now I'll step forward a line and another line. And go ahead and print that out. So let's print out x. So it incremented like we expected. And by the way, this x++ line has not been run yet. It's just showing me the line that will be run next. And I'm also going to print out p. And the pointer stayed the same. We didn't expect that to change. And I will jump down actually past, it says, okay, there's our error. I jumped down to the end essentially. And there's our error. It did not increment like we thought it would. But let's inspect our variables. Print x. Well, we know that's 7 because it printed to the screen. And inspect p. Here's our problem right here. Somehow, this pointer changed from 668 to 66C. Well, I guarantee you the original data did not get moved. So somehow we unintentionally modified our pointer. Well, let's go back to the code here. Actually, we'll stay here for a second. Here's the buggy line here. When I had added star p++, I thought I was dereferencing p and then incrementing it. But what I was doing was incrementing p, which is the pointer, and then dereferencing it. And that is because of the operator precedence in C++. It does the increment operator before it does the dereference operator. You might wonder why you would ever want to increment a pointer, but there are actually good reasons for it. And I'll probably make another video on pointer arithmetic and moving around in C arrays and C-style notation for arrays. So there are good reasons for it, but that is certainly not what we intended to do here. So to fix that, we can introduce parentheses. So I'll exit out of the debugger. I'll open our C file, our C++ file. And since I really want it to dereference first, I'll do that. It's typically, if you're in doubt, there's no harm in putting parentheses around it because you are clearly stating what your intentions are here. Oh, and the reason when we changed, what it was doing is incrementing the pointer, and when it dereferenced it, it just threw away the value that it dereferenced. We'll talk about what value it got when it dereferenced that messed up memory address in a second. But let's first see if this corrected it. Oops. All right, nice. All right, so I'm going to print out, I'm going to print this modified version of p out. Let's see what happens if we mess up the pointer. Dereferenced p+1 is, so I'm going to do p+1, and I will do star. And this would be the same if I did p++ and then did star. Actually, what we had before actually would have incremented it after it returned the value of p. So it actually would have returned 7 and done nothing with that. If I had done ++ p, we'd have gotten something else. But either way, I didn't do anything with the return value, so it doesn't matter. In this case, I am going to increment the pointer and dereference that and see what we get. So looks like in this case, we got some garbage. Now that's exactly what you're going to get. This is a very common bug. If you ever get garbage and you're dealing with pointers, you better make sure that you moved your pointer correctly, or if you're keeping track of your pointer, just make sure it's pointing to somewhere data actually exists. Another error you can get from a messed up pointer is a segmentation fault. It'll say segmentation fault core dumped. And that means you're pointing to somewhere completely invalid in memory. It looks like we were still somewhere valid in memory, but there's just garbage in there. So just be careful with pointers and keep an eye out for those kind of problems you can have. Okay, so now is a good time to ask, why do pointers even exist? Well, it'll make a lot more sense when you take a look at C-style arrays and C-style strings, because a lot of how they work involves the way they're laid out in memory. So if we can directly look inside of memory and move around inside of memory, it allows us to effectively manipulate the data the way it's actually stored. And C++ is a low-level language, so it makes sense that we should be able to directly interact with the way the computer's actually working behind the scenes. So the machine actually has RAM, and it's actually storing this data throughout the memory. So it makes sense that we should be able to access it where it is. Also, you need pointers in C++ to work with anything on the heap pretty much, because right here we just had stack variables, but whenever you use the new operator, you're returned a memory address, which refers to where that object is. You don't get the object itself, you just get a memory address of that object. So, for example, if I said person star p equals new person to create a new person object, this right-hand side of the equal sign is going to return the memory address of that person object. And you see over here, it's a pointer to a person, because that's exactly what I'm storing. And then if I wanted to call a method on p, I would need to dereference p and then call the method, so print info or something. Now, of course, I don't have this implemented, so this wouldn't work. And you'll also see sometimes this. So for objects that you actually have a pointer to that, this operation, this arrow operation, is exactly the same as dereference and dot. Exactly the same thing. So that's a place you'll use pointers a lot. Also, anytime you want to directly modify or directly access information, you need pointers. So say I wanted to write a function to increment a variable, and I have that right here. Here's a function to increment a variable. Normally in, say, Java, I don't have pointers, so I would have to just return the update. If I'm working with a primitive type like int, I would have to return the actual value. And so I'd have to pass a copy of the value in, return a copy of the value, and store that copied value into the original. Here in C++ and even C, we can pass in a pointer to the original, dereference it to directly modify it, and here I didn't have any need for assignment. So that can be handy. It also could be for performance reasons. Maybe you have an image that you're working with or some massive file. You don't want to be passing around copies of that file. You just want to pass around a pointer to where it exists in memory and directly access it. It's also worth noting that if you ever want to directly access a pointer, you need to step away from that pointer. In other words, get the memory address of that pointer. And that's where double pointers come into play. So say, let's go back to our person example. If I wanted somebody else to change what p points to, I wouldn't be able to just pass in p because nobody else could modify p directly. Well, I mean, I can right here in this scenario, but if I were passing it into another function, I'd actually need to pass in a pointer to p. So it would look like this: person star star p equals ampersand p. Now, you'll see that different places. It can mean any number of things. There are a lot of scenarios where you'd want a double pointer, maybe even triple pointers. It's more rare, but there's nothing wrong with having a pointer to a pointer, and so on. So I hope this lecture has been informative. The only way you're going to really get a good handle on this information is to get practice with it. So get in there and explore. You can even open the debugger while a program is running and try dereferencing things. Try changing variables. So do explore and see what happens as you move things around. Do keep in mind that the memory addresses will change as you're running it. But practice changing these things, and it can be really gratifying once you figure it out.